Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. We have been looking at some basics of the architecture. So, what we have been looking at so far is the following. We have looked at some basic operational concepts. We have looked at some understanding of how performance is measured. So, we looked at some performance measurement aspects, and we started looking at how to understand instructions. That is, what comprises an instruction and what is and how these instructions typically are organized. Okay, so we will look at some more details of this in today's lecture. So, to look at what is an instruction set, a review of instruction set as such. Instruction set is basically the repertoire of instructions of a computer. So, different computers could have different instruction sets, but with many aspects in common. That is, if you look at the instruction sets of different computers, different architectures, you will find that the instruction sets may differ, but you will find that there are many common aspects that are there. So, what we are now looking at is understanding those common aspects, and so that when you look at any particular architecture, you can understand the differences that exist and so on. Okay. So, we will just continue with understanding of the instruction set. Okay. So, what are the typical instructions that we have? We have already taken a look at this before, but just look at it again in order to understand to check our understanding. So, we talk about data transfer instructions, instructions like move, load, store and so on. Then we talk about arithmetic instructions, which are like add, subtract, multiply, divide, compare and so on. Then we talk about logical instructions, which perform logical operations such as AND, OR, XOR, NOT, shift. These are the kind of operations we have here. And then we talk about control instructions, instructions which do things like jump, branch, in the sense that you will be able to jump to a different address location, branch to a different address location. We also have variations of these jump and branch instructions like jump if not equal, branch if not equal, branch if greater than 0, different conditions that are there. And then we also talk about input output instructions, in and out instructions are typically used for these. Okay. So, these are the typical instructions that we talk about. So, if you look at instruction formats, again we have seen that instruction formats may vary, but in general an instruction would have the following parameters. Okay. So, and these components of an instruction that we talk about could be specified either explicitly or implicitly. Okay. Explicitly in the sense it would be there directly as part of the instruction, implicitly would mean that it is implied. Okay. Some part of this information may be implied and the rest of the information would be specified in an instruction. So, what is that you would have typically in an instruction? You would have the opcode, you would have the source operand. If there are two source operands, you will have source operand 1, you will have source operand 2, and then you would have the destination operand, and then if there is any control information that is required, that would also be specified. Again, the format of the instruction would depend on the architecture, but the content would cover most of these things. That is, you would have an opcode, source operand 1, source operand 2, destination operand, and some control information. Okay. So, this is what you would have typically in any instruction. And examples of instruction formats, we talk about what are called as 3 address instructions, 2 address instructions, 1 address instructions and so on. 3 address instructions, these are typically used in general purpose register based architectures. So, here what we talk about is we have instructions where 3 addresses, 2 addresses of the 2 source registers and one the destination register are all specified together. So, if I have an instruction like this, add R1, R2, R3, this would mean that the contents of R2 and the contents of R3 would be added and stored in the location R1 in this register R1. So, we have 3 addresses being specified here, it is called as a 3 address instruction. In a 2 address instruction, you would have something like this, you say add R1, R2. Here you can see that there are 2 addresses only specified R1 and R2, which means that one address is implied. For example, in this case we say that when we say add R1, R2, it actually means R1 is added to the contents of R2 and stored in R2. So, what is happening here is one of the source operands R1 is implied and that is also used as the destination operand. So, one address here serves as one of the source operands and one destination operand. So, that is what we have in this case of a 2 address instruction. If you have a 1 address instruction, you would have this typically happens in accumulator based architectures. So, here only one address is specified, which means that 2 other operands, 2 other values are all implied. So, if you take a look at this, for instance, add m, this is in an accumulator based architecture, which means that we would have an accumulator as a special purpose register, which is used as one of the source operands and the destination operand. So, you would have something like when you say add m, it means that I will take the memory locations of this memory address m, which is specified by m. So, I will take the contents of that memory location, add it to the value that is there in the accumulator and store that value in the accumulator. Okay. So, you can see that only one value is specified here, so it's a single address instruction, and 2 other values are implied, and in this case both of them happen to be accumulator, that is one source operand and the destination operand are both the accumulator. So, this is an example of a 1 address instruction. Next we can look at a 0 address instruction. So, this is typically used in stack based architectures. Okay. So, what do we mean by a stack based architecture? This is an architecture where I would have a stack which is used to store all the operands. So, in this case if I have an instruction like this, so add, now you can see that there is nothing else specified along with this add, no other addresses are specified. So, it is called as a 0 address instruction. Now, what does this mean? It means that all the operands are all there on that stack, that is the source operand is expected to be on the stack and the destination operand is also expected to be on the stack. So, look at what will happen here. So, here I would talk about TOS, that is top of stack. So, I would say I will take one of the operands from the top of stack, another operand from the top of stack minus 1, that is one which is below the top of stack. Now, these are the 2 operands that are taken, added together and the value is stored again back on the top of stack. Okay, this is the destination. So, you can see that all the 3, the position of the source operands and the destination operand are all implied. Okay, this is a totally all the 3 values, all the 3 addresses are implied. So, which is why we have a 0 address instruction which just says add. Okay. This is normally used only in stack based architectures. Okay. So, so you would have a, so as we this box here tells you that an instruction would normally consist of opcode and the operands or addresses, and this information, this operands or addresses as we have seen now may be implied or may be specified explicitly. We will just take a look at some examples of these. So, we will take a look at first a 3 address evaluation of a plus b into c plus d. Look at what will happen here. So, I would typically have an instruction add r1 comma a comma b, which would take the memory contents of a, memory contents of b and store it in location, some temporary location r1 let us say. And then I have another instruction add r2 comma c comma d, which will take c, d, these contents, add them, store them in r2. Now, we have got a plus b and c plus d in registers r1 and r2. Now, I need to have a multiply instruction which will take the values in r1 and r2, multiply them and store them in x. So, I have multiply x comma r1 comma r2. Remember our convention that we are using. The convention we are using is that the destination operand is specified first, followed by source operand 1 and then the source operand 2. So, when I say multiply x comma r1 comma r2, it means that x is the destination register, a destination value. So, in this case it happens to be a memory location. So, memory location x will have the destination value. What is the value that is stored over there? The contents of r1 multiplied with contents of r2. r1 into r2 is stored in this location. So, this is what happens, this is how 3 address instructions are used. Now, coming to our 0 address instruction, which happens to be in the stack based architecture. So, let us say again we take the same expression that is to be evaluated, that is I have evaluate a plus b into c plus d. Now, I am looking at 0 address instruction for this. Okay. So, what do I do now? Remember that we need to evaluate a plus b into c plus d. So, we need to have the operands pushed onto the stack and then we need to work from the stack. So, you have first an instruction called push a, which will push the contents of a onto the top of stack, and then I have an instruction called push b, which will push the value of b onto the top of stack. Okay. So, which means now a will be stored. So, it will be like this now. So, a would have been on the top of stack. Now, after this instruction a will go down and b will come on top of it. Okay. So, I have got a and b over here. Now, I specify an instruction called add. So, when this add instruction is specified, look at what will happen now. We said that whenever an add instruction is specified, there are no addresses specified along with it. So, 0 address instruction. So, the no address is specified, which means that the values will be taken from top of stack and top of stack minus 1. Top of stack will give me B, top of stack minus 1 will give me A. So, both these values will be taken, added, and the result will be stored again back on the top of stack. So, this is what will happen with respect to this add. Now, what I do is, so now what will happen, both A plus B would be gone, and what will be stored on top of stack will be A plus B here. Okay. So, now push C, next I want to do C plus D. So, how do I do that? I push C, which means contents of C are now moved to the top of stack. So, C will be added here. Then I have a push D. So, contents of the location D will be pushed on top of stack. So, this will be added over here. So, you got A plus B, you got C, and then you got D on top of that. Okay. So, now when I do add, okay, so what happens here now? C plus D will be added, that is top of stack and top of stack minus 1. D has top of stack, C is there in top of stack minus 1. So, both these are added and that value is stored back at the top of stack. So, what will happen now will be, let me cut this out, you will have A plus B here, and on top of that you will have C plus D that is stored. So, now if I do a multiply operation now, look at what this mul will do. This will take the operand which is there at the top of stack, which is C plus D, and then I have got A plus B which is below that. Both these values will be now multiplied, and you can see that that value will be there available on the top of stack. And then I have a pop x which will store this value which is there on the top of stack to the memory location x. So, you can see that both these operations, the add and mul, are examples of the zero address format where all the information is taken from the stack. Okay. So, which means that all the operands have to be pushed to the stack. So, that is something which needs to be done. Okay. So, which is why we normally have push and pop instructions which are used. So, push is used to push it onto the stack, pop is used to pop it from the stack, and in this case the push and pop operations are taking place from memory to stack and from stack to memory. So, this is what would happen in a stack based architecture. So, to come back to our instructions now, typical instructions that we normally face, okay, or use. So, let us look at this typical set of instructions that we have. So, we said we talk about data movement instructions, arithmetic instructions, shift instructions, and logical instructions, and so on. Okay. So, let us take a look at some of the common uses of these instructions. So, data movement instructions, we normally have instructions which like load and store. So, a load instruction normally is used to get data from memory to a register. Store is used to move data from a register to memory. Then you could also have a memory to memory move. You can also have a register to register move, and you can have an input operation or an output operation. An input instruction normally moves data from an IO device to a register or memory, and similarly an output instruction would move data from the register or memory location to an output device. Okay. Similarly, we have push and pop instructions which are used to move data to the stack or from the stack. Okay. So, these are examples of the data movement kind of instructions. Arithmetic instructions, this we have this we are very familiar with. We have integer or addition instructions, subtract instructions, multiply or divide. Now, these add, subtract, multiply and divide could work either with integer instructions, either it could be binary or in decimal, or with floating point or fixed point instructions. Both these are possible. Other than that, we have shift instructions which are used to shift left, shift right, rotate left, rotate right, and so on. Similarly, logical operations such as not, and, or, the normal usual logical operations. Plus, you also have instructions which can be used to set a bit or a clear a bit, and so on. So, these are typical instructions that are provided. So, if we look at the other instructions that we have, we talk about control instructions, and control instructions normally are jump or branch instructions are used, and they may be conditional instructions or unconditional instructions. That is, it may be an unconditional jump or branch. So, it could just be a simple jump instruction which jumps to a particular location, or it can be a conditional instruction where you would say jump if some value is greater than 0, or jump if something is less than 0, and so on. Okay. So, these are called as conditional instructions. Other than this, we have instructions which take care of subroutine linkage when a subroutine is called, for instance. So, you have instructions like call, and you have a return which will return from the subroutine. Similarly, there are instructions for interrupt. So, you have an instruction called a trap which is used to start an interrupt operation, and then you can have these are what we refer to as software interrupts. So, you can have an interrupt instruction which is done by means of a trap instruction, and then again there would be a return which would be a return from an interrupt. Normally, we distinguish between return from interrupt and return from a normal call to a subroutine. So, which is why we have two returns specified over here. Other than this, there are also instructions which are provided for synchronization purposes. We have what are called as test and set instructions, which are used to test a value, and then if based on the test you set it to a particular value. So, these are called as atomic read, modify, write operations. So, atomic in the sense that you will read a value, modify the value and write the value as if the whole thing is taking place in an undivided manner. You are reading something, modifying that value and then doing a write operation, but all these three will take place as if they were one single instruction, that is they were one undivided operation. Okay. So, no other operations can take place in between these three operations. Okay, that is called, and these are instructions which are used normally for synchronization purposes. We will look at the uses of these later. Then there are instructions which will do string based operations, like for instance search, translate and so on, or string comparison kind of instructions are provided. And then depending on some special purpose architectures that may be available, you may have for instance graphics related instructions, which is there normally in an MMX kind of architecture, which are used for doing some parallel sub operations, parallel additions, parallel multiplications and so on. Okay. So, these are the typical instructions that we have. So, we will take a break now and then come back and continue after the break. Okay. Welcome back after the break. So, we have been looking at general information about instructions. Now, when we talk of instructions, we also talked about using memory locations, right. We said that the operands could be memory locations or registers. Now, when it is a memory location, we need to understand about how these memory locations are organized and how they are addressed. So, which is what we will look at now. When we look at memory locations, we know that memory basically consists of some storage cells. In fact, memory consists of many millions of storage cells, each of which can store 1 bit. Okay. But we do not normally look at memory as bitwise addressing, but we normally look at memory addressed in terms of a group of bits. So, we look at n bits for instance grouped together as a single word in memory. Okay. So, which is why we normally look at memory organized in terms of words and bits within the words. Okay. So, data as we said is usually accessed in n bit groups, and this n is normally called as the word length. Okay. So, which is why we would, if you look at memory as a whole, it would consist of many words, okay, first word, second word and so on, and the ith word and the last word, and each word is a n bit can store n bits of information. Okay. So, this is what we normally have. Okay. Now, coming to how we address this, how we take care of these addresses and so on. So, we said that so let us take a look at a 32 bit word as an example. Okay. So, now we said that we said memory locations are basically n bits, right. So, this n can be anything, it can be 8 bits, 16 bits, 32 bits and so on. So, we are looking at a 32 bit word length example to understand how it is stored. So, what will happen now, if I take a 32 bit word for instance, so I will have bits B0 to B31 that can be stored. Okay. So, B0 to B31 can be stored in a 32 bit word, and if a signed integer is being stored in this 32 bit location, so what we will have here is the bits B0 to B30 would be the magnitude, or if it is a signed magnitude representation that is used, this would specify the value that you have, and this B31, the last bit normally is used to specify the sign bit. It would be a 0 for positive numbers and it would be a 1 for negative numbers. Again, depending on whether you are using 2's complement representation or 1's complement representation or sign and magnitude representation, which are normally used for representing signed numbers, the contents of B0 to B30 would vary. What is commonly used is a 2's complement representation. So, B0 to B30 would have the value that we have, and the B31 would specify the sign bit. Now, the same 32 bits could be used for storing characters, and a character typically is stored in 8 bits. So, if you have an 8 bit ASCII character for instance is stored, you can see that since we have 32 bits available over here, 4 ASCII characters could be stored in this particular 32 bit location. Okay. A single location can host 4 ASCII characters. So, depending on what is the data that is stored, the organization would vary. Okay. So, this is what we need to understand. So, now to retrieve information from memory, what is it that we need to do? So, to retrieve information from memory, either for one word or one byte, okay, which is 8 bits as we know. So, addresses are required for each location. So, we said that we have so many different locations, right. So, each location is normally given one address, And how do we address it? Either we can say each word is given an address, or you could say that each byte in a word is given an address. Okay. Normally what we do is we normally give addresses to the byte, so we say it is a byte addressable memory. Okay. So, in general let us understand how we identify the addresses and the number of bits that are required for specifying the addresses. So, in general you can see that a k bit address memory can have 2 power k memory locations, okay, and these are named normally from 0 to 2 to the power of k minus 1. Okay. So, which is what we normally refer to as the memory space. So, which means if I have a 24 bit memory, that means I can go from up to 2 to the power of 24 different locations can be addressed. So, 2 power 24, which is 16 meg. Okay. So, we normally refer to 2 power 20 as 1 meg, that is, it is approximately 10 to the power of 6. Okay. So, it is 16 into 10 to the power of 6 locations that can approximately be addressed by a 24 bit memory. If it is a 32 bit memory, that means I can go from 2 to the power of, I can go up to 2 to the power of 32, which means 0 to 2 to the power of 32 minus 1 will be the distinct addresses that we use. So, in this case you would go up to 2 to the power of 32, which is approximately 4 gig, 4 to 10 to the power of 9. Remember, 2 to the power of 1 meg is 10 to the power of 6, 1 gig is 10 to the power of 9, which is approximately 2 to the power of 30. In fact, it is exactly 2 to the power of 30 and approximately 10 to the power of 9. So, 4 gig is 4 times 1 gig. Okay. So, that is what can be addressed using a 32 bit memory. Similarly, if I had 10 bits that I used, I will be able to go up to 1 kilo, 1 k, 2 power 10. If I had 40 bits instead, I could go up to 1 tera byte of memory or tera locations that can be specified. Okay. So, whenever we talk about memory locations, we need to be familiar with these terms that we use. That is, we talk about kilobytes, we talk about megabytes, we talk about gigabytes, and we talk about terabytes. Then on top of that we also have petabytes and so on, but these are the common terms that we are normally using. Okay. So, as we said, it is normally not practical to assign distinct addresses to individual bit locations in memory, right. So, we, as I said, we normally give addresses to words or bytes in memory. Okay. So, most commonly used mechanism is the byte addressable mechanism. So, we talk about byte addressable memory locations. Okay. So, when we use byte addressable memory locations and we actually have words being used, okay. So, what we also need to understand then is how is it that the bytes within each of the words are addressed. So, we say byte locations have addresses 0, 1, 2 if the word length is 32 bits. Then successive words are located at addresses 0, 4, 8 and so on. Okay. So, byte locations we say have addresses 0, 1, 2 etc. If the word length is 32 bits, then the successive words are located at addresses 0, 4, 8 and so on. So, why do we say this? Because we know that if I have a word length of 32 bits, then there can be 4 bytes that can be accommodated in that. So, if my addresses are for the bytes that are there, so 4 bytes will be there in single word. So, 0, 1, 2, 3 would be the words that would be the bytes that are there in the first word or the 0th word. So, the next word will now have byte location starting from 4, 5, 6, 7 and so on. So, if it has byte location starting from 4, 5, 6 and 7, so the next word address would be at 4. Similarly, the next word address will start at 8 and so on, right. So, this word addressing and byte addressing is something that you need to understand. Okay. So, when we talk of this kind of a word and byte addressing, there is one other aspect that we need to understand, which is the order in which the bytes are stored within the word. Okay. So, here we normally refer to 2 different address assignments. One is called the big endian address assignment and the other is called the little endian assignment. Okay. So, what we mean in a big endian assignment is that if I take a word, okay, in the word the lower byte address are used for the most significant bytes of the word. Okay. So, if you look at it like this is the word that I have. Now, this is word address 0. So, the lower byte addresses are used for the most significant bytes of the word. So, this is my most significant byte in this word. So, the 0th address the byte address 0 actually specifies the is used for the most significant byte address within this word. Okay. So, you will have addresses given like this. So, byte address here will be 0, this address of this byte will be 1, this address byte will be 2, this byte's address will be 3 and so on. Okay. So, and this word has an address of 0. Okay. So, next word again will start with the word address is 4 and the way the bytes are organized within this are byte address 4 is here, 5 is here, 6 is here, 7 is here and so on. This is called the big endian addressing assignment. The opposite of this is called the little endian addressing assignment, where the lower byte addresses are used for the less significant bytes of the word. That is, if I take this to be my least significant byte, so least significant byte gets also the lower address, that is least significant byte has an address of 0, next byte has a value of 1, next is address with 2, next is address with 3 and so on. This entire word you can see is addressed as word 0. In word 0, least significant byte will get a value, will get an address of 0, next byte will have a value of 1, next byte will have a value of 2, next byte will have a value of 3 and so on. So, in the next word which is addressed with location 4, which starts at location 4, so 4, 5, 6, 7 will be stored in this order. You can see that between these two, between the big endian and the little endian mechanism, the order of bytes within a word are reversed. Okay? That is the difference that we need to understand, because you can see that since the order is reversed, if the words are stored in this order, but you actually read it in this particular format, then you will get the inverse of the data that you have actually stored. You will not get the correct data that is stored. So, I must always be aware of what is the assignment that is used when memory addresses are used, especially when you have larger words with number of bytes that are stored within them. We should know whether we are using big endian addressing or little endian addressing. So, depending on whether we are using big endian or little endian, you will have to interpret the data accordingly. And what is also to be noted is that many different architectures, they follow different assignments. Okay. Some architectures follow a big endian assignment, some architectures follow a little endian assignment. So, now, so when you have data being transferred between two different machines which are working with two different architectures, which have two different assignments, for instance, we have to be careful about how the data is transferred. So, this is normally a problem that we have when data is transferred across networks, which is why when we transfer data across networks, we bring it to some standard format and then move it from that standard format to any of these different assignments. So, remember that we have these two different big endian and little endian assignments that are used. Okay. Okay. So, now quickly summarizing what we are looking at in terms of memory locations and addresses. So, what is important to remember here is word alignment. Okay. So, as we said, let me look at the second point first. The second point I have written here is that we are using memory locations to store or access numbers, characters and character strings, all these are used. Okay, this is something that we remember. Now, the next thing we need to look at is how are the words aligned in memory. That is, we say that the words are aligned in memory if they begin at a byte address, that is a multiple of the number of bytes in a word. Okay, for instance, if I have a 16-bit word, now we know that 16-bit word, the addresses, word addresses are all 0, 2, 4 and so on. So, if I am looking at addressing a location which starts at 0, 2, 4 or a multiple of 2, then we say that this particular memory location, that address that we are looking at, is aligned to the way it is stored in memory. So, because we know that it is stored in memory in groups of 0, 1, 2, 3, 4, 5 and so on, if you are accessing address in the same manner, then you say that you are doing an aligned address, aligned access of the data from memory. Okay. So, we say that the way the data is stored is also, it is aligned to the words. Instead, if I store the data as, for instance, suppose I take data 1 and 3 and store it and look at it as stored in location 0 and 1. So, you will find that the alignment will not be there, or for instance, let me put it differently. For instance, if I say that I am trying to access a location 1 and location 3. Now, where would location 1 and location 3 be, byte 1 and byte 3? They are actually a part of the 0th location and a part of the second location. Okay. So, I would if I am accessing location 0 and 1, I can do it in a single access of by accessing one word, 0 and 1 I will get it directly. But if I am accessing locations 1 and 2, now what will happen is I will have to take part of the data from location 0 and part of the location from data from location 2. So, you will actually be doing two accesses to memory, right. So, this is a problem when we do misaligned memory access, but if you do an aligned access, it will get over in a single access. Okay. So, now we can look at what will happen in a 32-bit word and a 64-bit word. So, 32-bit word, similarly you will have 4 different locations will be there. So, 32-bit word addresses are aligned if they start at locations 0, 4, 8 and so on. Similarly, 64-bit word addresses are aligned if they start at 0, 8, 16 and so on. Okay. So, this is how the address alignment has to be understood. Okay, so to summarize on the memory operations that we normally do, okay, we need to understand addressing, and then we need to understand the operations that we do on memory. So, we know that there are two operations that we do on memory, one is a load and one is a store. So, load is typically a read or a fetch. So, what do we do in a load, read or fetch? You are copying the content from memory location. So, the memory content does not change. What we need to specify for this is address is to be specified and registers are used to store the location. In case of a store, you are overwriting the content in memory. So, both address and data need to be specified in this case, and again registers can be used to store the data. Okay. So, this is what we need to understand with respect to memory locations and how memory operations are performed. Okay. So, to summarize, what we have looked at in today's lecture are basically two things. One is that we have looked at understanding instructions. So, we have looked at this 3 address, 2 address, 1 address and 0 address instructions and so on, and we looked at different types of instructions. This is what we did in the first half. The second half we will try to understand how data is stored in memory and how the memory addresses are handled. Okay. So, these are two things that we have tried to look at in today's lecture. So, a few questions for you to look at the material that we have understood today. List 10 commonly used instructions. Question number 2, what is the characteristics of instructions in a stack based architecture? Question number 3, what is the difference between big endian and little endian addressing? 4, give examples of control transfer instructions. So, these are 4 questions that will help you to review today's material. Thank you.